Sound cannot travel through empty space. Every astronaut knows this. In the vacuum between stars, you could scream as loud as you want and nobody would hear you. Sound needs air. Ocean waves need water. Every wave you have ever encountered in your life needs some kind of substance to move through. Take that substance away and the wave dies. But light does something that should be impossible. It crosses millions of miles of pure emptiness without any medium at all. Right now, photons from stars that died before Earth existed are sailing through the void between galaxies, through regions where there is not a single atom for trillions of miles, and they arrive here perfectly intact. No air, no water, no substance of any kind, just empty space. So what exactly is waving, and how can nothing carry something? Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. You have heard waves your entire life. Even if you have never thought about them scientifically, even if you have never opened a physics textbook, you know what a wave is. You have felt the bass from a speaker vibrate through your chest at a concert. You have watched ocean waves roll toward the shore and break into white foam. You have clapped your hands in a quiet room and heard the echo bounce back from the walls. Waves are everywhere. They are one of the most familiar phenomena in the natural world, so common that we barely notice them. But there is something about waves that most people never stop to think about. Something so basic, so obvious, that it hides in plain sight. Every wave you have ever experienced in your daily life has one thing in common. Every single one of them needs something to travel through. And when you truly understand why that matters, you begin to see why light is one of the most puzzling things in the universe. Let us start with sound, because it is the wave you encounter most often. Right now, as you listen to these words, sound waves are traveling from your speakers or headphones into your ears. But what exactly is happening? What is a sound wave, really? When a speaker produces sound, the driver inside the speaker pushes forward. That push compresses the air directly in front of it, squeezing the air molecules closer together into a region of higher pressure. Those compressed molecules then push on the molecules next to them, which push on the molecules next to them, and so on. The compression travels outward from the speaker like a chain reaction, spreading through the room in every direction. Behind the compression, the air molecules spread apart again, creating a region of lower pressure called a rarefaction. The pattern of compression followed by rarefaction followed by compression again is what we call a sound wave. It is a pressure disturbance rippling through the air. Here is the critical thing to understand. The air molecules themselves do not travel from the speaker to your ear. They do not fly across the room. They just jostle back and forth in place, each one bumping into its neighbour, passing the vibration along. What actually travels across the room is the disturbance, the pattern of squeezing and stretching. The wave moves through the air, but the air itself stays more or less where it was. Think about a line of dominoes standing on a table. When you knock over the first one, it hits the second, which hits the third, and the falling pattern travels down the entire line. But the dominoes themselves do not travel, they just fall in place. Each individual domino only tips over right where it was standing. The wave of falling travels across the table, the dominoes do not. Sound works in a very similar way. The disturbance propagates, the medium stays put. And this brings us to the most important point about sound. Without air, there is no sound. No air molecules means nothing to compress and stretch, nothing to jostle against its neighbour, nothing to pass the vibration along. The wave simply cannot exist without the material it moves through. The medium is not optional. It is everything. This is not just theory. It has been demonstrated in laboratories since the 1600s. Robert Boyle performed one of the earliest versions of this experiment around 1659. The setup is beautifully simple. You place a small ringing bell inside a glass jar. You can hear it clearly through the glass. The bell vibrates. The air inside the jar carries the sound to the glass walls. The glass vibrates. The air outside the jar carries it to your ears. The chain of transmission is unbroken. Then you start pumping the air out of the jar, creating a vacuum inside. As the air disappears, molecule by molecule, the ringing gets quieter and quieter and quieter, until eventually you cannot hear it at all. The bell is still vibrating. You can see it moving. Its clapper is still striking the sides. But with no air molecules inside the jar to carry the vibration from the bell to the glass, the sound cannot reach you. The wave has lost its medium, and without its medium, it ceases to exist. This is why there is no sound in space. In science fiction movies, you hear explosions in space, you hear engines roaring, you hear lasers firing with dramatic whooshing sounds. None of that would actually happen. Space is a near-perfect vacuum. In the regions between planets, you might find a handful of particles per cubic centimetre, mostly from the solar wind. In deep interstellar space, the density drops even further. In the vast voids between galaxy clusters, there might be fewer than 1 atom per cubic metre. That is not enough material to carry a sound wave of any kind. An astronaut floating outside the International Space Station could bang 2 metal rods together as hard as they wanted, and the only sound they would hear would be what travelled through their spacesuit and the air sealed inside their helmet. Nothing would travel through the vacuum surrounding them. Absolute silence. The emptiness of space cannot carry sound because sound is a vibration of matter, and there is no matter there to vibrate. Sound waves are what physicists call mechanical waves. They are mechanical because they require a physical medium, a material substance to propagate through. Air is the most common medium for sound in our everyday lives, but sound can also travel through liquids and solids. In fact, it travels faster and more efficiently through denser, more rigid materials. Sound moves through air at about 343 meters per second at room temperature. Through water, it moves at about 1,480 meters per second, more than 4 times faster. Through steel, it moves at about 5,960 meters per second, more than 17 times faster than in air. The denser and more rigid the material, the faster the vibration passes from one molecule to the next, because the molecules are packed tighter and respond more quickly to being pushed. This is why whales can communicate across entire ocean basins. A blue whale's low-frequency call can travel thousands of miles through the water because the ocean provides an excellent medium for sound propagation. The water molecules are packed much closer together than air molecules, so the compressions pass along faster and with less energy loss. The ocean is like a superhighway for sound waves, but the same rule always applies. Take away the water and the wave dies. No medium, no wave. That is the rule. Now let us look at another kind of wave you know well. Ocean waves. When you stand on a beach and watch waves rolling in toward the shore, what you are really seeing is energy moving through water. Somewhere out at sea, perhaps hundreds or even thousands of miles away, a storm pushed on the ocean surface. Wind transferred energy to the water. That energy created a disturbance, a pattern of rising and falling on the surface. And that pattern propagated outward from the storm, travelling across vast stretches of open ocean until it reached your beach. But here is something most people do not realise. The water itself is not travelling from the storm to the beach. If you dropped a cork in the middle of the ocean and watched it as a wave passed underneath, the cork would bob up and down in a roughly circular motion, rising as the crest passed, falling as the trough followed, and then ending up almost exactly where it started. The water molecules move in circles. They do not travel horizontally with the wave. What moves across the ocean is the shape, the pattern of rising and falling. The disturbance propagates. The water stays in place. The medium carries the wave by passing the disturbance from one bit of material to the next, each molecule nudging its neighbour, but none of them actually going anywhere. Without the water, the ocean wave cannot exist. This seems almost silly to state out loud. Of course you cannot have an ocean wave without an ocean. That is like saying you cannot have a ripple without a pond. The wave is a disturbance of the water. Remove the water and there is nothing left to disturb. The wave is not a thing that exists on its own. It is something the medium does. Seismic waves work the same way. When an earthquake occurs deep underground, the sudden release of energy sends vibrations through the Earth's crust and interior. These vibrations travel through solid rock, sometimes for thousands of miles. Primary waves, which arrive first at seismograph stations, compress and stretch the rock in the direction the wave travels, similar to how sound compresses air. Secondary waves move the rock side to side, perpendicular to the direction of travel. Surface waves roll along the ground, like ocean waves roll along the water's surface, and these are usually the ones that cause the most damage during an earthquake. But all of them, every type of seismic wave, need the rock and soil of the Earth to travel through. Without the solid ground beneath your feet, seismic waves cannot exist. The medium is essential. Even the wave you do at a sports stadium follows this exact pattern. When fans in one section stand up and raise their arms, the people next to them see this and do the same thing a moment later, and the wave of standing and sitting ripples around the stadium. It looks like something is travelling around the arena, and something is. A disturbance, a pattern. But the fans themselves stay in their seats. The fans are the medium. Each person passes the disturbance to their neighbour. Without the fans, there is no stadium wave. Without the medium, there is no wave. So here is the rule that emerges from every wave you have ever encountered in your entire life. Waves are disturbances that travel through a physical medium. The medium can be air, water, rock, metal, or even a crowd of people. But there must be something there, some physical substance, some material, for the disturbance to propagate through. Remove the substance and the wave cannot exist. It is not weakened, it is not slowed down, it is gone. This seemed like a fundamental truth about the universe. It seemed like one of those rules that had no exceptions. And then there was light. Light does something that no other wave in our everyday experience does. It travels through completely empty space. Right now, light from the sun is crossing about 150 million kilometers of vacuum to reach the Earth. Between the sun and the Earth, there is almost nothing. A sparse scattering of solar wind particles, some cosmic dust. But for all practical purposes, it is empty. And yet sunlight crosses that enormous void in about 8 minutes and 20 seconds, arriving with enough energy to warm the planet, drive the climate, and power nearly all life on Earth. Nothing carried it, nothing supported it, nothing passed it along from molecule to molecule the way air passes along sound. The light just travelled through emptiness. And this is not limited to the short distance between the sun and the Earth. Light from distant stars travels for years through the vacuum of interstellar space. The nearest star beyond our Sun, Proxima Centauri, is about 4.24 light-years away. The light you see from that star tonight has been travelling through empty space for more than 4 years. During that entire journey, those photons encountered almost nothing. They crossed regions where the density of matter is so low it would make the best vacuum we can create in any laboratory on Earth look positively crowded by comparison. Go even farther. The light from galaxies billions of light-years away has been crossing the void of intergalactic space for billions of years. These photons have travelled through the emptiest regions in the known universe, the enormous voids between galaxy clusters where you might find only a handful of hydrogen atoms in a volume the size of a living room. And still, the light arrives. It is fainter because it has spread out over such a staggering distance. Its wavelength has been stretched by the expansion of space, but it arrives. The wave propagated successfully through trillions upon trillions of miles of virtually perfect vacuum, with no medium of any kind to support it. This created a tremendous problem for physicists. By the early 1800s, scientists had strong evidence that light behaves as a wave. The debate between particles and waves had been going on for over a century. Isaac Newton, in his 1704 work on optics, had argued that light is made of tiny particles, which he called corpuscles. These particles travelled in straight lines, bounced off mirrors, and explained many of light's observed behaviours. Newton's enormous reputation gave this particle theory tremendous weight for decades. But the Dutch physicist Christiaan Huygens had proposed an alternative. In 1678, Huygens argued that light is a wave. He showed that a wave theory could explain reflection and refraction, the bending of light as it passes from one material to another, just as well as Newton's particles could. For a long time, the two theories competed, with Newton's particle theory dominating mainly because of Newton's prestige. Then, in 1801, Thomas Young performed an experiment that changed everything. Young's double-slit experiment sent a beam of light through two narrow slits cut in an opaque barrier. On a screen behind the barrier, instead of seeing two bright lines, one behind each slit, Young observed a pattern of alternating bright and dark bands spread across the screen. This is an interference pattern, and it is something only waves can produce. When two wave crests arrive at the same point on the screen at the same time, they reinforce each other and create a bright band. When a crest from one slit arrives at the same time as a trough from the other, they cancel each other out and create a dark band. Particles cannot do this. Particles would simply pile up behind each slit, creating two bright patches. The interference pattern was decisive evidence that light is a wave. Augustin-Jean Fresnel, a French physicist working in the early 1800s, developed Young's ideas further with rigorous mathematics. He showed that the wave theory of light could explain not just interference, but also diffraction, the bending of light around obstacles and through small openings. By the middle of the 1800s, the wave theory of light was firmly established. Virtually every physicist accepted that light is a wave. But if light is a wave, then by every principle physicists understood at the time, it must need a medium. Sound is a wave in air. Ocean waves are waves in water. Seismic waves are waves in rock. If light is a wave, what is it waving in? What is the medium that light vibrates as it crosses the emptiness between the sun and the earth? The answer scientists came up with was ingenious, reasonable, and ultimately wrong. They proposed that all of space is filled with an invisible, weightless, perfectly transparent substance called the luminiferous ether. The word luminiferous means light-bearing. The ether was supposed to be the medium through which light waves propagated, just as air is the medium through which sound propagates. It seemed logical. Every known wave had a medium. Light is a wave. Therefore, light must have a medium too. They called it the ether, and they set about trying to detect it. But the ether had to have some truly remarkable properties to do its job. It needed to fill all of space, permeating everything, occupying every gap between every atom and every star and every galaxy. It needed to be perfectly transparent, because we cannot see it or feel it. It needed to be essentially massless, because it did not seem to affect the motions of planets orbiting the Sun, or moons orbiting their planets. Gravitational calculations worked perfectly, without accounting for any drag from the ether. And it needed to be incredibly rigid, because the speed of a wave through a medium depends on the stiffness of that medium. Sound travels faster through steel than through air, because steel is far more rigid. Light travels at about 300,000 kilometers per second. For the ether to support a wave at that tremendous speed, it would need to be extraordinarily stiff, far stiffer than diamond, far stiffer than any material known to exist. These requirements were deeply contradictory. How can something be stiffer than diamond and yet offer no resistance to objects moving through it? The planets orbit the Sun for billions of years without slowing down. If they were ploughing through a substance stiffer than diamond, they should grind to a halt almost immediately. Yet the ether needed to be exactly this paradoxical combination of extreme rigidity and perfect permeability. It was starting to sound less like a real physical substance and more like a convenient fiction, a name for something nobody could find. But physicists pressed on because they saw no alternative. The logic seemed airtight. Light is a wave. Waves need media. Therefore, the ether must exist. The challenge was simply to detect it. In 1887, two American physicists, Albert Michelson and Edward Morley, designed what would become one of the most famous experiments in the history of science. Their reasoning was beautifully straightforward. If the ether fills all of space, and the Earth moves through it as it orbits the Sun, then the Earth must be ploughing through the ether like a ship through calm water. The Earth orbits the Sun at about 30 kilometers per second. That means there should be an ether wind blowing past the Earth at that speed, just as you feel a wind when you drive with the car window down, even if the air outside is perfectly still. If the ether wind exists, it should affect the measured speed of light. Light travelling in the same direction as the Earth's motion through the ether should appear slightly slower, like a swimmer going upstream. Light travelling in the opposite direction should appear slightly faster, like a swimmer going downstream. Light travelling perpendicular to the ether wind should have a different speed still. The differences would be tiny, fractions of a percent, but Michelson had invented an instrument sensitive enough to detect them. That instrument was an interferometer. It split a beam of light into two perpendicular paths of equal length, sent each beam out to a mirror and back, then recombined them. If one path was aligned with the ether wind and the other was perpendicular, the two beams would return slightly out of sync. One would have travelled slightly faster than the other, and this timing difference would create a shift in the interference pattern when the beams were recombined. A measurable, visible change in the bands of light and dark. Michelson and Morley mounted the entire apparatus on a massive stone slab, floating in a pool of mercury, so they could rotate it smoothly to test different orientations. They isolated it from vibrations. They ran the experiment over and over. They tried different times of day, when the Earth's rotation pointed the apparatus in different directions. They tried different seasons, when the Earth was at different points in its orbit, and therefore moving through the ether from different angles. The result was always the same. Nothing. No shift. No difference. No ether wind. Zero. The speed of light was identical in every direction, regardless of how the Earth was moving through space. There was no detectable ether wind, which meant either the ether was behaving in some extraordinarily strange way, or it simply was not there. This result stunned the physics community. Michelson and Morley had built the most sensitive instrument they possibly could, designed specifically to detect the one thing the ether must produce if it existed, and they found nothing. It was one of the most important null results in the history of science. They went looking for the ether with every tool available, and the ether refused to appear. Some physicists tried to save it. The Irish physicist George Fitzgerald and the Dutch physicist Hendrik Lorentz independently proposed that objects moving through the ether physically contract in the direction of motion by exactly the amount needed to cancel out the effect Michelson and Morley were looking for. This was a clever mathematical rescue, but it felt like a patch, an assumption added specifically to explain why the experiment failed. The rescue attempts grew more and more elaborate, each one requiring new assumptions to explain why the ether existed, but could never, under any circumstances, be detected. In 1905, Albert Einstein took a radically different approach. Rather than trying to explain why the ether could not be found, he simply discarded it entirely. His special theory of relativity started from two principles. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source. There was no mention of the ether, no invisible substance filling space, no cosmic medium. Einstein showed that you did not need any of it. Light travels at a fixed speed through empty space, and that speed does not change no matter how fast you are moving or in which direction. But discarding the ether left the original problem wide open, and now it was even more urgent than before. We know light is a wave. Young's experiment proved it produces interference patterns. Fresnel's mathematics confirmed it. We know it travels through empty space. Every observation of sunlight and starlight confirms this, and we know there is no invisible substance filling space for it to wave through. Michelson and Morley proved that beyond any reasonable doubt. So what is happening? What is waving? How can a wave exist in emptiness? The answer is that we were asking the wrong question all along. For centuries, physicists had assumed that all waves must be vibrations of a physical substance, because every wave they had ever studied was exactly that. Sound waves are vibrations of air molecules. Ocean waves are vibrations of water. Seismic waves are vibrations of rock. Every familiar example pointed to the same conclusion. Waves need stuff. Waves need material. Waves need a medium. But this assumption contained a hidden error. Scientists were generalizing from mechanical waves and assuming that all waves must work the same way. They were looking at sound and water and earthquakes and concluding that every wave in the universe must be a disturbance of some physical material. And then, when they encountered a wave that did not seem to need material, they invented an invisible, undetectable material rather than questioning the assumption itself. They preserved the rule by inventing something to satisfy it, rather than considering the possibility that the rule might have an exception. The real question was never what substance carries light through empty space. The real question is what light is actually a disturbance of. What is the thing that is vibrating, oscillating, changing as a light wave passes through the void? And the answer to that question is not a substance at all. It is something entirely different, something that can exist in empty space, far from any matter, far from any atoms or molecules. Something invisible and intangible, yet absolutely real, measurable, and fundamental to how the universe works. Light is a disturbance of electric and magnetic fields, and understanding what that means, understanding how fields can exist in the vacuum, how they can change and oscillate and regenerate each other as they race across the cosmos, that is what changes everything. Because once you see it, the question flips. It stops being about how light travels through nothing. It becomes about what empty space truly is. And the answer turns out to be far stranger and far more beautiful than any invisible substance could ever be. To understand how light can travel through empty space, you need to understand something that is invisible, silent, and yet absolutely everywhere around you right now. Fields. Electric fields and magnetic fields. These two things are the key to everything. They are the answer to the question we have been building toward. But most people have never really thought about what a field is, because you cannot see one with your naked eye. You cannot touch one with your fingers, and nobody teaches you about them in a way that makes them feel real. They sound like abstractions, like mathematical ideas drawn on a chalkboard, like arrows on a diagram in a textbook that are useful for calculations, but do not correspond to anything you could actually encounter in the physical world. That understanding is completely wrong. Fields are real. They are as real as the chair you are sitting in, as real as the air you are breathing, as real as the ground beneath your feet. They exist in physical space. They carry energy. They exert forces. They can do work on objects. And most importantly for our story tonight, they can exist in places where there is no matter at all. Fields can exist in a perfect vacuum, in the emptiest regions of space, far from any atom, any molecule, any substance of any kind. This is the property that makes everything else possible. Let us start with the electric field, because it is the easier one to build intuition about. Take a single proton, a positively charged particle sitting alone in otherwise empty space. Not in air, not in water, not inside an atom. Just a proton floating in a vacuum, completely by itself. Is the space around that proton truly empty? In one sense, yes. There are no other particles nearby. There is no material substance surrounding it. If you could somehow look at the space around that proton with impossibly powerful eyes, you would see nothing at all. But now imagine you take a second charged particle, say an electron, and you bring it into the region around the proton. The electron does not need to touch the proton. It does not need to be anywhere near the proton. It can be far away. And yet, the moment you place that electron in the surrounding space, it feels a force. It is pulled toward the proton. An attractive force acts on it immediately, tugging it in the direction of the positive charge. The electron accelerates. It moves. Something is pulling on it. And that something is acting across empty space, across a gap that contains nothing at all. What is doing the pulling? This is the question that fascinated physicists for centuries. In the 1600s and 1700s, the standard answer was something called action at a distance. The proton simply reaches across space and tugs on the electron, instantly, with no mechanism, and no explanation for how the force gets transmitted. Charles-Augustin de Coulomb formalized this idea in 1785 with his inverse square law, showing that the force between two charged particles is proportional to the product of their charges and inversely proportional to the square of the distance between them. Double the distance, and the force drops to 1/4. Triple the distance, and it drops to 1/9. The mathematics was clean and precise, and it matched every experiment perfectly. But it left a deeply uncomfortable question unanswered. How does the proton know the electron is there? How does the force get transmitted across the gap? There is nothing between them. No rope, no string, no mechanism. The proton just somehow reaches across empty space and pushes or pulls on anything with a charge. And it does so instantaneously, at the exact moment the other charge appears. This bothered a lot of physicists, but the math worked so well that most of them set the discomfort aside and moved on. Then came Michael Faraday, and he changed everything. Faraday was one of the most extraordinary scientists in history, and his story is remarkable because he had almost no formal education. He was born in 1791 in South London to a poor family. He received only basic schooling and was apprenticed to a bookbinder at the age of 14. But while binding books, he read them. He was particularly fascinated by the science books that came through the shop. He read about electricity and chemistry and became obsessed. He attended public lectures by the famous chemist Humphrey Davy at the Royal Institution and took meticulous notes. Eventually he talked his way into a position as Davy's laboratory assistant, and from there he rose to become one of the greatest experimentalists the world has ever known. Faraday could not do advanced mathematics. This was considered a serious limitation at the time, and it caused many of his more mathematically inclined peers to look down on his ideas. But his lack of mathematical training forced him to think in pictures, in physical intuitions, in mental models of what was actually happening in the space around charged objects and magnets. And this turned out to be an enormous advantage, because it led him to an insight that changed physics forever. Faraday proposed that a charged particle does not simply reach across space and pull on other charges. Instead, a charged particle creates something in the space around it. It modifies the space itself. The space surrounding a charge is different from the space far away from any charge. Faraday called this modification a field, the electric field. Every charged particle is surrounded by an electric field that extends outward in all directions, filling the space around it, getting weaker with distance, but never entirely disappearing. The field is there whether or not a second charge is present to feel it. It is not a response to another charge, it is a property of the space surrounding the first charge. Faraday visualized these fields as lines of force radiating outward from positive charges and converging inward toward negative charges. He drew them in his notebooks, beautiful flowing curves filling the space around charged objects. The lines were denser close to the charge, where the field is strong, and spread farther apart at greater distances, where the field is weaker. These were not just mathematical conveniences for Faraday. He believed the lines were real. He believed the field was a genuine physical entity filling the space around charged objects. This was a radical shift. Before Faraday, the space between two charges was considered truly empty, nothing but a gap across which forces somehow acted. After Faraday, the space between two charges was filled with something, the field. The field is not matter. It is not made of atoms or molecules. It has no mass in the traditional sense. You cannot bottle it or weigh it on a scale. But it is there. It occupies space. It has a strength and a direction at every single point, and it is what transmits the force. In Faraday's picture, the proton does not reach across space and pull on the electron. Instead, the proton creates an electric field in the space around it. That field exists everywhere, extending outward in all directions, filling the vacuum. When the electron enters this field, the electron interacts with the field at its own location. The field pushes on the electron right where the electron is. The force is local. The electron responds to the field in its immediate vicinity, not to the distant proton. The proton and the electron never directly interact. They each interact with the field, and the field mediates the force between them. Now let us turn to magnetic fields, because they are the other half of this story, and they work in a remarkably similar way. You have probably played with magnets at some point in your life. You know that magnets attract certain metals. You know that two magnets can attract each other or repel each other, depending on which ends you bring together. If you have ever held two strong magnets close together and felt that invisible push or pull between them, you have felt a magnetic field at work. A magnet creates a magnetic field in the space surrounding it. Like the electric field, the magnetic field extends outward in all directions, filling the space around the magnet. The field is strongest near the poles and weaker farther away. And here is the critical point. The magnetic field exists in the empty space around the magnet, not in the magnet itself. Well, it exists inside the magnet too, but it also extends outward into the vacuum surrounding it. If you placed a magnet in a sealed chamber and pumped out every last molecule of air, the magnetic field would still be there. You could prove this by bringing another magnet or a piece of iron nearby and watching it respond. The field fills the vacuum just as readily as it fills air or water. It does not need a substance to support it. Faraday demonstrated this with his famous iron filings experiments. He placed a magnet under a sheet of paper and sprinkled iron filings on top. The filings align themselves along the magnetic field lines, revealing the beautiful curving pattern of the field. The curves sweep from one pole to the other, arching through space, creating a pattern that is both elegant and deeply informative. The filings do not create the field, they simply make the field visible. The field was there before the filings were sprinkled. The field would be there if no filings existed at all. The filings are just a tool for seeing something that is otherwise invisible. This is the first great insight. Electric and magnetic fields are real physical things that exist in empty space. They are not substances. They are not made of atoms, but they are absolutely real. They fill the vacuum. They carry energy. They exert forces on charged particles and magnets. A region of empty space with a strong electric field in it is physically different from a region of empty space without one. The field is something, and it is something that does not require matter to exist. But Faraday was just the beginning. The truly revolutionary discoveries came next, and they involved the relationship between electric fields and magnetic fields. Because these two fields are not independent, they are deeply and fundamentally connected, and that connection is the reason electromagnetic waves can exist. The first clue came in 1820, when the Danish physicist Hans Christian Ørsted made a startling discovery during a lecture demonstration. He was showing his students an experiment with electric current flowing through a wire when he noticed something unexpected. A compass needle sitting on the table near the wire deflected. It swung away from magnetic north and pointed toward the wire. When he reversed the direction of the current, the needle swung the other way. Ørsted realized that the flowing electric current was creating a magnetic field. This was astonishing. Before this moment, electricity and magnetism were considered entirely separate phenomena. Electric charges produced electric forces. Magnets produced magnetic forces. They were two different things that happened to coexist in the universe, like sound and light, related only in the sense that they were both forces acting at a distance. Ørsted's experiment showed they were connected. An electric current, which is simply a flow of electric charges, produces a magnetic field in the space around it. Electricity creates magnetism. The French physicist André-Marie Ampère jumped on this discovery and developed it further. Ampère showed that the magnetic field from a current-carrying wire wraps around the wire in circles. The field does not radiate outward from the wire like the electric field radiates from a charge. Instead, it curls around the wire, forming concentric loops. The direction of the field depends on the direction of the current. Ampère formalized this into precise mathematical laws and showed that the magnetic field could be calculated exactly from the current and the geometry of the wire. So electricity can create magnetism. But does the reverse work? Can magnetism create electricity? Faraday spent years searching for this reverse effect. He knew that a steady current creates a steady magnetic field. He wondered whether a steady magnetic field could create a steady current. He tried placing magnets near wires, near coils of wire, near every arrangement he could think of. Nothing happened. A steady magnetic field, no matter how strong, produced no current in a nearby wire. Then in 1831, Faraday made the discovery that would change the world. He found that a changing magnetic field does produce an electric current. When he pushed a magnet through a coil of wire, a current flowed in the wire while the magnet was moving. When he stopped moving the magnet, the current stopped. When he pulled the magnet back out, a current flowed again, but in the opposite direction. It was not the presence of the magnetic field that created the current, it was the change. A magnetic field that is getting stronger or getting weaker or changing direction induces an electric field that can drive charges through a wire. A steady magnetic field does nothing. A changing magnetic field creates an electric field. This discovery is called electromagnetic induction, and it is the principle behind virtually every electrical generator on the planet. Every power plant, whether it runs on coal, natural gas, nuclear energy, wind, or hydroelectric power, generates electricity by moving magnets relative to coils of wire. The changing magnetic field creates an electric field, which pushes electrons through the wires, producing the current that powers your lights, your appliances, your phone, your entire modern life. Faraday's discovery in 1831 is arguably the single most practically important discovery in the history of science. But for our purposes tonight, the practical applications are not the point. The point is the deep physical principle. A changing magnetic field creates an electric field. Not just in wires, not just in metals. A changing magnetic field creates an electric field in empty space. The wire is not necessary. If a magnetic field is changing in some region of the vacuum, an electric field appears there. The field creates the field. No matter is required. No atoms, no electrons, no conductors. Just empty space and a changing magnetic field, and an electric field is born. Now here is where things become truly extraordinary. James Clerk Maxwell, a Scottish physicist working in the 1850s and 1860s, took everything that was known about electricity and magnetism and assembled it into a unified mathematical framework. Maxwell was a theoretical physicist of staggering ability, often ranked alongside Newton and Einstein as one of the greatest minds in the history of science. He took the experimental discoveries of Faraday, Ørsted, Ampere, and others, and expressed them as a set of precise mathematical equations. In the process of doing this, Maxwell noticed something. The equations as they stood were incomplete. There was a mathematical inconsistency, a situation where the laws of electricity and magnetism, as they were understood at the time, contradicted each other. The existing laws said that a changing magnetic field creates an electric field. That was Faraday's discovery. But the equations did not include a corresponding reverse process for electric fields. There was an asymmetry. Changing magnetism creates electricity, but the mathematics had no term for changing electricity creating magnetism. Maxwell realized that to make the equations mathematically consistent, he needed to add a new term. He proposed that a changing electric field also creates a magnetic field. This was not based on experiment. No one had observed this effect directly. It was a theoretical prediction, a correction Maxwell added because the mathematics demanded it. He called it the displacement current, and he added it to the equations governing magnetic fields. This addition was one of the most profound insights in the history of physics, because now the relationship between electric and magnetic fields was perfectly symmetrical. A changing magnetic field creates an electric field, and a changing electric field creates a magnetic field. Each one generates the other. They are locked together in a reciprocal relationship, each one capable of bringing the other into existence. Think about what this means. Imagine you have a changing electric field in some region of empty space. That changing electric field creates a magnetic field nearby. But now that magnetic field is also changing, because it just came into existence. And a changing magnetic field creates an electric field, which is also changing, which creates another magnetic field, which is changing, which creates another electric field. Each field generates the other, which generates the first, which generates the other, in an endless, self-sustaining chain. This is not a cycle that stays in one place. Each newly created field appears a little farther out from where the last one was. The electric field creates a magnetic field slightly ahead of itself. That magnetic field creates an electric field slightly farther ahead, and so on, and so on. The disturbance moves outward through space. It propagates, not through a substance, not through a medium, through the fields themselves, each one regenerating the other, leapfrogging forward through the vacuum at a speed determined by the fundamental properties of empty space. Maxwell worked out the speed. He calculated it from the known constants that governed electric and magnetic fields, constants that had been measured in laboratory experiments involving capacitors and inductors, experiments that had nothing to do with light. And the number he got was approximately 300,000 kilometers per second, the speed of light. This was a thunderbolt. Maxwell had started with the laws of electricity and magnetism, added one correction term for mathematical consistency, and the equations told him that electromagnetic disturbances should propagate through empty space at exactly the speed of light. The correspondence was too precise to be a coincidence. Think about what had just happened. A man sitting at a desk with a pen and paper, working through equations about magnets and electric charges, had just derived the speed of light. He had not measured light. He had not performed any optical experiment. He had not used prisms or mirrors or lenses. He had simply taken the known laws of electricity and magnetism, noticed a mathematical gap, filled it in, and the speed of light fell out of the equations unbidden. Two entirely separate branches of physics, optics and electromagnetism, which had been studied independently for centuries by different people, using different instruments, asking different questions, turned out to be the same thing. It was as if someone studying the rules of music theory and someone studying the rules of ocean tides had suddenly discovered they were writing the same equations. Maxwell wrote, with characteristic understatement, that the agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. Light is an electromagnetic wave. It is not a vibration of air or water or some invisible ether. It is a vibration of electric and magnetic fields. These fields exist in empty space. They do not need a substance to support them because they are not vibrations of a substance. They are vibrations of the fields themselves. And the fields can exist in a vacuum because fields are not matter. They are a different kind of physical reality, one that does not require atoms or molecules, one that can fill the emptiest regions of the cosmos without any material support. This is the fundamental difference between electromagnetic waves and every other wave you have ever encountered. Sound is a vibration of air molecules. Remove the air and the vibration stops. Ocean waves are vibrations of water molecules. Remove the water and the vibration stops. But an electromagnetic wave is a vibration of electric and magnetic fields, and you cannot remove the fields from space. They are part of what space is. Fields are not something added to the vacuum like furniture placed in an empty room. They are more like a property of the room itself. The vacuum of space inherently supports electric and magnetic fields. That capability is built into the fabric of reality. This is why the ether was never found. There was nothing to find. Scientists were searching for a mechanical substance, something made of matter, something they could poke and prod and detect with instruments. But the medium of light is not a substance. It is the field structure of empty space itself. The vacuum is not nothing. It is something. It has properties. It can support fields. It can carry energy. But it is not a material in any ordinary sense. It is not made of atoms. It is not a gas or a liquid or a solid. It is the arena in which fields exist and through which field disturbances propagate. And that arena needs no additional substance to do its job. Think about it this way. When Ørsted discovered that an electric current creates a magnetic field, he did not discover that the current creates a magnetic substance. The magnetic field is not made of anything in the way that a rock or a glass of water is made of something. The field is a condition of space. It is a state that space can be in. Space near a current-carrying wire is in a different state from space far away from any current. The difference between those states is what we call the magnetic field. And that state, that condition, can exist in a perfect vacuum just as easily as it can exist in air or water. The same is true for electric fields. An electric field is not a substance. It is a condition of the space surrounding a charged particle. The space near a proton is in a different state from the space far from any charge. That difference is the electric field. And changing from one state to another, oscillating between different configurations of electric and magnetic field, is what an electromagnetic wave is. The wave is not a vibration of stuff, it is a vibration of state. The state of the fields at each point in space changes, oscillates, and that oscillation propagates forward as each changing field generates the next one. This is genuinely difficult to wrap your head around if you have spent your entire life thinking of waves as vibrations of material things. Every intuition you have built from watching ocean waves and hearing sound waves tells you that something must be physically moving, physically jostling, physically vibrating. And in electromagnetic waves, something is vibrating. The electric and magnetic field strengths are oscillating, but the thing that is vibrating is not a substance, it is a field, and fields do not need material to exist. Faraday imagined this. He imagined his lines of force as real physical things filling the space around charges and magnets. Most of his contemporaries thought he was being naive, that the lines were just mathematical tools, useful pictures that helped with calculations but did not correspond to physical reality. Maxwell proved Faraday right. The fields are real, they exist in empty space, and they can sustain a self-propagating wave that carries energy across the cosmos without any material medium at all. When Maxwell published his complete electromagnetic theory in 1865, he had unified electricity, magnetism, and optics into a single framework. Three phenomena that had seemed completely separate turned out to be different aspects of the same underlying physics. Electric forces, magnetic forces, and light itself were all manifestations of electric and magnetic fields and their interactions. It was one of the greatest unifications in the history of science, rivaled only by Newton's unification of terrestrial and celestial gravity, and Einstein's later unification of space and time. But the full significance of Maxwell's achievement goes even deeper than unification. Maxwell showed that the universe contains a kind of physical reality that is fundamentally different from matter. Fields are not made of particles. They are not composed of atoms. They do not have mass in the same way a rock or a planet does. And yet, they are absolutely real. They carry energy. They exert forces. They propagate disturbances at the speed of light. They are, in a very meaningful sense, what fills the universe between the particles of matter. They are the invisible infrastructure of reality, the hidden framework that makes forces possible, that makes light possible, that connects charged particles across empty space, and carries energy from stars to planets across trillions of miles of vacuum. And the mutual creation of electric and magnetic fields, the reciprocal dance where each one generates the other, is the engine that makes it all work. Without that relationship, electromagnetic waves could not exist. If a changing electric field did not create a magnetic field, the chain would break. The disturbance would die out as soon as it left the source. If a changing magnetic field did not create an electric field, same thing. The wave would collapse. It is only because both directions of creation work, only because the relationship is perfectly symmetrical, that the disturbance can sustain itself and travel indefinitely through the vacuum of space. That symmetry is not a coincidence. It is a deep truth about the structure of the universe. Electricity and magnetism are not two separate forces that happen to interact. They are two aspects of a single force, electromagnetism, and the relationship between them is what gives rise to light itself. The wave that crosses the void between the stars, the light that has travelled for billions of years from the most distant galaxies, the warmth you feel on your face when you step into the sunshine, all of it exists because a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, in an endless, self-sustaining dance that needs nothing but empty space to continue. Now that we understand the pieces, the electric field and the magnetic field, and the fact that each one can create the other, we need to see how those pieces fit together to form something truly remarkable. A wave that builds itself as it goes, a disturbance that needs no push from behind, no pull from ahead, no medium to carry it. A wave that once started will travel forever through empty space until something absorbs it. This is what an electromagnetic wave is, and understanding how it works is one of the most beautiful things in all of physics. Let us build it from scratch. Imagine a single charged particle, say an electron, sitting in otherwise empty space. It has an electric field surrounding it, extending outward in every direction. That field is static, meaning it is not changing. It is just sitting there, steady and constant. A static electric field does not create a magnetic field. Nothing is happening. The fields are quiet. Now imagine you suddenly jerk that electron upward. You grab it and accelerate it sharply in one direction. The electric field around the electron has to adjust. The field cannot adjust everywhere simultaneously, because changes in the field propagate at the speed of light, not instantaneously. Close to the electron, the field updates quickly to reflect the new position. Far away, the field still looks like the electron is in its old position, because the information about the change has not arrived yet. This creates a kink in the field, a disturbance, a region where the field is rapidly changing from its old configuration to its new one. That kink propagates outward at the speed of light, like a ripple spreading from a stone dropped in a pond. Here is where Maxwell's insight becomes critical. That kink is a region of rapidly changing electric field. And what does a changing electric field do? It creates a magnetic field. So now, embedded in that outward moving kink, a magnetic field appears. But this magnetic field is also changing, because it just came into existence, and it is part of a propagating disturbance. And what does a changing magnetic field do? It creates an electric field, which is also changing, which creates another magnetic field, and the chain continues. The electric field does not need the original electron anymore. Once the kink has left the vicinity of the charge, it is on its own. The changing electric field creates a magnetic field. The changing magnetic field creates an electric field. Each one regenerates the other. The disturbance sustains itself, carrying energy away from the source and through the vacuum of space. The electron gave the wave its initial push, its birth. But from that point forward, the wave is self-sufficient. It does not look back. It does not need the source to keep feeding it. It races outward at the speed of light, an autonomous disturbance in the fields of empty space. This is fundamentally different from any mechanical wave. A sound wave in air is sustained by the air. Every compression pushes on the next layer of molecules, which pushes on the next, and if you remove the air at any point along the path, the chain breaks and the wave dies. The wave depends on the medium at every point in its journey, from source to destination, with no gaps allowed. An electromagnetic wave depends on nothing but the fields themselves, and the fields are not a medium in the traditional sense. They are not a substance that was there before the wave arrived and remains after it passes. The fields are the wave. The oscillating electric and magnetic fields are not something the wave travels through. They are the wave itself. Think about it this way. In a sound wave, the air exists before the wave comes and after the wave passes. The wave is a temporary disturbance of a pre-existing substance, but in an electromagnetic wave, the oscillating fields are the disturbance. In the moments before the wave arrives at a given point in empty space, the electric and magnetic fields at that point are zero, or whatever their background values happen to be. When the wave arrives, the fields at that point begin to oscillate, rising and falling in a precise pattern. When the wave passes, the fields return to their previous state. The wave brought the oscillation with it and took it away when it left. The fields did not sit there waiting to be vibrated, like air molecules waiting for a sound wave. The wave created the oscillation and carried it forward through the self-generating process of changing fields producing more changing fields. Let me try to make this more vivid, because this is the single most important idea in everything we have discussed, and it deserves to be seen clearly. Imagine a vast, dark, completely empty stretch of space. No atoms, no dust, no gas, nothing. Now imagine that at one end of this stretch, something disturbs the electric field. Maybe a charged particle accelerated violently, maybe an electron in a distant star changed energy levels. It does not matter what caused it. What matters is that the electric field at that location is now changing. It is rising and falling, oscillating. At the point right next to that oscillation, there was no magnetic field a moment ago. But now one appears, conjured into existence by the changing electric field beside it. This new magnetic field did not travel from somewhere else. It was not carried in by any substance. It was born right there at that exact point in the vacuum, because the laws of electromagnetism say that a changing electric field must produce a magnetic field in the neighbouring region of space. The universe has no choice in this. It is not optional. It is as mandatory as gravity pulling a dropped stone toward the ground. Now that magnetic field is itself changing because it just appeared where there was none before. It is growing, oscillating, varying in strength. And that changing magnetic field does the same thing to the space beside it. It creates an electric field one step farther out. That electric field is also changing, and so it creates a magnetic field one step farther still, and on and on. Each field reaching into the next patch of empty space and calling the other field into existence. No runner carries a baton from one point to the next. No chain of molecules passes a vibration from neighbour to neighbour. There is no material out there at all. There is only the rule, the law, the deep structural fact about our universe that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. That rule operates at every point in the vacuum. It does not require matter to enforce it. It does not need atoms to execute it. It is a property of space itself, as intrinsic as the fact that space has 3 dimensions. Wherever the rule operates, and it operates everywhere, a self-sustaining electromagnetic wave can propagate. The wave creates the conditions for its own next step as it goes, laying down the road it travels on, one oscillation at a time, advancing at the speed of light through regions that contained absolutely nothing before the wave arrived. This self-sustaining nature means electromagnetic waves can travel indefinitely through empty space. There is no friction to slow them down. There is no medium to absorb their energy. There are no molecules jostling and losing energy to heat. In a perfect vacuum, an electromagnetic wave will travel forever, maintaining its frequency and its speed, crossing any distance the universe allows. The only things that can stop it are absorption by matter or the expansion of space stretching its wavelength. But in a straight path through empty vacuum, with nothing in the way, the wave just keeps going. This is why we can see galaxies billions of light years away. The light left those galaxies billions of years ago and has been self-sustaining ever since, crossing the vast emptiness of intergalactic space without any material support. Now let us talk about the speed of this wave, because this is one of the most remarkable parts of the entire story. When Maxwell derived his equations and found that electromagnetic disturbances should propagate as waves, the speed of those waves was not something he put in by hand. He did not assume the speed. He calculated it from 2 numbers that had already been measured in completely unrelated experiments. Those 2 numbers are the electric permittivity of free space and the magnetic permeability of free space. These are properties of the vacuum itself. They describe how empty space responds to electric and magnetic fields. The electric permittivity, called epsilon naught, tells you how strongly the vacuum resists the formation of an electric field. A higher permittivity means the vacuum is harder to polarize electrically. The magnetic permeability, called mu naught, tells you how readily the vacuum supports a magnetic field. These are not properties of any material. They are properties of emptiness. They describe the electromagnetic character of the vacuum, the way empty space itself interacts with fields. Epsilon naught had been measured through experiments with capacitors, devices that store electric charge. By measuring how much charge a capacitor could store at a given voltage, physicists determined how the vacuum responds to electric fields. Mu naught had been measured through experiments with electromagnets and current-carrying wires, determining how the vacuum responds to magnetic fields. These measurements were done in laboratories using wires and metal plates and sensitive instruments. They had nothing to do with light. Nobody measuring epsilon naught was thinking about stars or sunshine or the nature of light. They were just trying to understand how capacitors work. But when Maxwell combined these two constants in his equations, he found that the speed of electromagnetic waves is equal to 1 divided by the square root of epsilon naught times mu naught. He plugged in the measured values and got approximately 300,000 kilometers per second, the speed of light. The implications of this are staggering. The speed of light is not some arbitrary cosmic speed limit chosen at random. It is determined by the electrical and magnetic properties of empty space. The vacuum itself dictates how fast electromagnetic waves travel. If the vacuum had a different permittivity or a different permeability, light would travel at a different speed. The speed of light is a property of the vacuum, encoded in the way empty space responds to electric and magnetic fields. It comes from the fabric of reality itself. This also tells us something deep about what the vacuum is. Empty space is not featureless nothingness. It has measurable properties. It has an electric permittivity and a magnetic permeability. These numbers are not zero. They are specific, finite, measurable values. The vacuum has electromagnetic character. It responds to fields in specific, quantifiable ways. And that response determines how fast disturbances in those fields can propagate. But here is what makes this even more extraordinary. The vacuum's properties do not make it a substance. Having measurable properties does not make something a material. Temperature is a measurable property, but temperature is not a substance. Pressure is a measurable property, but pressure is not a substance. The vacuum has properties, but it is not made of stuff. It does not have atoms. It does not have molecules. It is not a solid, liquid, or gas. It is something else entirely, a kind of physical reality that supports fields and their disturbances without being a material medium. This is why the ether search was always doomed to fail. Scientists were looking for a substance, a thing made of particles, a physical material filling space. But the vacuum's ability to carry electromagnetic waves does not come from any substance. It comes from the vacuum's intrinsic properties, from what empty space simply is. Let us now talk about what the electromagnetic spectrum actually is, because this is where the story expands from a single phenomenon into something that touches every part of your life. When Maxwell showed that light is an electromagnetic wave, he also showed something just as important. Light is not the only electromagnetic wave. The equations do not specify a frequency. They do not say electromagnetic waves must oscillate at the frequencies our eyes can detect. They say electromagnetic disturbances of any frequency will propagate through the vacuum at the speed of light. There is no lower limit and no upper limit on the frequency. Any oscillation of electric and magnetic fields, no matter how fast or how slow, will produce a self-sustaining wave that travels at 300,000 kilometers per second through empty space. This means there should be an entire spectrum of electromagnetic waves, most of them invisible to human eyes, filling the universe with radiation we cannot see. And that is exactly what we have found. At the lowest frequencies, we have radio waves. These are electromagnetic waves with frequencies ranging from about 3 Hz to 300 GHz, corresponding to wavelengths from thousands of kilometers down to about 1 millimeter. Radio waves were first produced and detected in a laboratory by Heinrich Hertz in 1887, about 2 decades after Maxwell predicted their existence. Hertz built a simple transmitter, essentially a spark gap that created a rapidly oscillating current, which generated rapidly changing electric and magnetic fields, which propagated outward as electromagnetic waves. Across the room he placed a receiver, a loop of wire with a small gap. When the electromagnetic waves reached the receiver, the oscillating fields induced a current in the wire, producing a tiny spark across the gap. Hertz had transmitted energy across empty space using electromagnetic waves. No wires, no air molecules carrying the signal, just fields propagating through the vacuum between the transmitter and receiver. This experiment was the first direct confirmation of Maxwell's prediction. Electromagnetic waves existed beyond the narrow band of visible light. They could be generated and detected, and they travelled at the speed of light, exactly as Maxwell's equations predicted. Hertz measured the wavelength and frequency of his waves and confirmed that their speed matched the speed of light to within experimental precision. Within a decade of Hertz's experiments, Guglielmo Marconi figured out how to use radio waves for long-distance communication, and the age of wireless communication was born. Every radio broadcast, every television signal, every Wi-Fi connection, every cell phone call, every satellite communication, every Bluetooth device, every radar system, all of them use electromagnetic waves. They all work because changing electric and magnetic fields regenerate each other and propagate through space without needing any material to carry them. When you make a phone call, the electromagnetic wave carrying your voice does not travel through the air like sound does. It travels through the electromagnetic field structure of the space between your phone and the nearest cell tower. The air has nothing to do with it. If you could remove every molecule of air between your phone and the tower, the signal would still get through. It is not a sound wave. It is a field disturbance propagating through the vacuum-like properties of space. Moving up in frequency from radio waves, we reach microwaves. These have frequencies between about 300 MHz and 300 GHz. Your microwave oven uses electromagnetic waves at a frequency of about 2.45 GHz. These waves cause water molecules in your food to vibrate, converting electromagnetic energy into thermal energy. The electromagnetic wave enters the food. Its oscillating electric field pushes on the water molecules. Those molecules rotate back and forth billions of times per second, and the friction of that rapid motion generates heat. You are literally cooking your food with electromagnetic waves, with the same fundamental phenomenon that carries light from distant stars. Higher still, we find infrared radiation. This is electromagnetic radiation with frequencies just below what your eyes can detect. Your body emits infrared radiation constantly because you are warm. Anything with a temperature above absolute zero emits electromagnetic radiation, and for objects near room temperature, most of that radiation is in the infrared range. When you hold your hands near a campfire and feel the warmth on your skin, even though you are not touching the flames, you are feeling infrared radiation. Electromagnetic waves are traveling from the fire to your skin, carrying energy across the gap of empty air. William Herschel discovered infrared radiation in 1800 by placing a thermometer just beyond the red end of the visible spectrum produced by a prism. The thermometer showed a temperature increase, even though there was no visible light falling on it. Something invisible was carrying energy beyond the red edge of the rainbow. That something was electromagnetic waves at frequencies too low for human eyes to detect. Then comes visible light, the narrow band of the electromagnetic spectrum that human eyes can see. This band spans wavelengths from about 380 nanometers for violet light to about 700 nanometers for red light. Out of the entire electromagnetic spectrum, which spans wavelengths from thousands of kilometers to fractions of the diameter of an atomic nucleus, our eyes respond to a sliver so thin it seems almost absurdly narrow. If the electromagnetic spectrum were a piano with keys stretching from one side of the United States to the other, the visible portion would be about the width of a single key somewhere near the middle. Everything else, radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, is invisible to us. We are almost entirely blind to the electromagnetic universe. Beyond violet light, at higher frequencies and shorter wavelengths, lies ultraviolet radiation. This is the radiation from the sun that causes sunburns. It has enough energy per photon to damage the chemical bonds in your DNA, which is why prolonged exposure increases the risk of skin cancer. Johann Ritter discovered ultraviolet radiation in 1801 by showing that invisible radiation beyond the violet end of the spectrum could darken silver chloride, a chemical reaction that visible light also causes, but that occurred even more rapidly with the invisible radiation beyond violet. At still higher frequencies, we find X-rays. Wilhelm Röntgen discovered X-rays in 1895 and almost immediately recognized their medical potential. X-rays have enough energy to pass through soft tissue, but are absorbed by dense material like bone, which is why X-ray images show your skeleton in stark white against the darker silhouette of your body. X-rays are electromagnetic waves. They are the same fundamental phenomenon as the radio waves carrying your favorite music, just at enormously higher frequencies. The same self-sustaining dance of electric and magnetic fields, oscillating trillions of times faster. At the highest frequencies of all, we find gamma rays. These are the most energetic electromagnetic waves, produced in nuclear reactions, in matter-antimatter annihilation, in the cores of collapsing stars, and in the violent neighborhoods of black holes. Gamma-ray photons carry so much energy that they can smash apart atomic nuclei. The gamma-ray burst from a collapsing star can release more energy in a few seconds than the Sun will produce in its entire 10 billion-year lifetime. And that energy is carried by electromagnetic waves, by the same self-regenerating field disturbance that also carries the gentle warmth of a campfire and the quiet signal of a Wi-Fi router. All of these, from radio waves to gamma rays, are the same thing. They are all electromagnetic waves. They are all self-sustaining disturbances of electric and magnetic fields propagating through space at the speed of light. They differ only in frequency, in how rapidly the fields oscillate. A radio wave oscillates perhaps a few million times per second. Visible light oscillates about 500 trillion times per second. A gamma ray might oscillate 10 billion trillion times per second. But the underlying mechanism is identical. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. The chain repeats and the disturbance moves forward. This universality is one of the most elegant features of electromagnetism. One set of equations, Maxwell's equations, governs all of it. The same four equations that describe the static electric field around a charged balloon also describe the gamma rays streaming from a supernova. The equations do not care about the frequency. They do not have special cases or exceptions. Every electromagnetic wave in the universe, from the lowest frequency radio wave to the highest energy gamma ray, obeys the same laws and propagates by the same mechanism. The universe is surprisingly economical in its principles. Now let me address something that often causes confusion. When we say that electromagnetic waves carry energy through empty space, what does that actually mean? Where is the energy? In a sound wave, the energy is in the motion of the air molecules, in their kinetic energy as they jostle back and forth, and in the pressure variations that store potential energy. But in an electromagnetic wave, there are no molecules. There is no matter. So where is the energy? The energy is in the fields themselves. Electric and magnetic fields store energy. This is not some abstract mathematical statement. It is a physical fact with measurable consequences. Every electric field contains energy proportional to the square of the field strength. Every magnetic field contains energy proportional to the square of its strength. A region of space where the electric or magnetic field is strong contains more energy than a region where the fields are weak. The energy is distributed throughout the space where the fields exist. In an electromagnetic wave, the electric and magnetic fields oscillate. As the electric field reaches its peak, it stores maximum electric energy. A quarter cycle later, the electric field passes through zero, while the magnetic field reaches its peak, storing maximum magnetic energy. The energy sloshes back and forth between the electric and magnetic fields, trading between them as the wave oscillates. But the total energy in the wave remains constant at any given point in the cycle. Energy is conserved. It just shifts between the two field types. This energy is real. It can be extracted and used. When sunlight falls on a solar panel, the oscillating electric field in the light wave pushes on the electrons in the semiconductor material, driving them through a circuit, generating electricity. The energy was in the electromagnetic wave, stored in the oscillating fields, and the solar panel extracted it by letting the fields do work on charges. The energy travelled 93 million miles from the Sun through the vacuum of space, carried entirely by oscillating electric and magnetic fields, with no material involved at any point in the journey. Electromagnetic waves also carry momentum. This seems strange because they have no mass, and in everyday life, momentum is something you associate with moving objects, with bowling balls and trucks and thrown baseballs. But electromagnetic waves push on things. When light hits a surface, it exerts a tiny but real pressure. This radiation pressure has been measured in laboratories and is used in theoretical proposals for solar sails, spacecraft that would be pushed through space by the pressure of sunlight. The pressure is very small, about 4.5 millionths of a pascal for direct sunlight at Earth's distance from the Sun, but it is real and it is measurable. A wave with no mass, no substance, no material of any kind, travelling through empty space, exerts a physical force on objects it encounters. The energy and momentum are in the fields. This is what makes the vacuum so remarkable. It is not a substance, but it supports field disturbances that carry energy and momentum. It has measurable electromagnetic properties that determine how fast those disturbances travel. It allows the self-regenerating dance of electric and magnetic fields that makes light possible. The vacuum is not nothing, but it is also not something in the way that a rock or a glass of water or a cloud of gas is something. It is a different category of physical reality, a stage with built-in properties that allow certain kinds of performances to take place on it. And electromagnetic waves are the performances. When we say empty space carries an electromagnetic wave, we are not saying empty space is a hidden substance like the ether. We are saying that the physical properties of the vacuum, its permittivity and permeability, allow electric and magnetic fields to exist and to sustain self-propagating disturbances. The fields are not vibrations of the vacuum, the way sound is a vibration of air. The fields are their own thing, a category of physical reality, distinct from matter, capable of existing in the absence of any substance. The vacuum does not carry electromagnetic waves the way a river carries a boat. The vacuum simply allows electromagnetic waves to exist, the way empty space allows objects to move through it. You do not need a substance to fill the gap. You just need the gap to have the right properties, and our vacuum does. Maxwell could not have known it at the time, but his equations revealed something about the architecture of reality that goes far deeper than any single experiment. They showed that the universe contains more than matter. It contains fields. And those fields are not lesser entities, not second-class citizens compared to atoms and molecules. They are fundamental. They carry energy. They carry momentum. They propagate disturbances at the speed of light. They connect charges across empty space. They fill the vacuum with invisible structure. And when they oscillate, when they dance their self-sustaining dance of mutual creation, they produce the phenomenon we call light, the phenomenon that allows us to see, that warms our planet, that carries information from the farthest reaches of the cosmos to our telescopes and our eyes. The electromagnetic wave does not need a medium because it is its own medium. It creates the conditions for its own propagation as it travels. Each oscillation of the electric field generates the magnetic field that generates the next electric field that generates the next magnetic field, leapfrogging forward through empty space forever. It is one of the most self-sufficient phenomena in all of nature. Born from a single disturbance of a charged particle, it detaches from its source and races across the universe at 300,000 kilometers per second, carrying energy and information, needing nothing but the bare fabric of space itself to continue its journey. And every form of electromagnetic radiation, from the radio waves that carry your music to the gamma rays that pour from dying stars, works by this same beautiful, self-sustaining mechanism. Everything we have discussed so far, the electric field creating a magnetic field, the magnetic field creating an electric field, the self-sustaining wave racing through empty space at 300,000 kilometers per second, all of this is the classical picture. It is Maxwell's picture, and it is correct. It describes how electromagnetic waves propagate with extraordinary precision. Engineers use Maxwell's equations every day to design antennas, fiber optic cables, satellite communications, and medical imaging systems. The classical picture works beautifully, but it is not the complete picture. In the early 20th century, physicists discovered something about light that Maxwell's equations alone could not explain, something that seemed to contradict the wave picture entirely. And understanding this deeper layer of reality reveals something even more profound about what empty space truly is. The trouble started in 1900 when the German physicist Max Planck was trying to solve a problem about how hot objects radiate energy. Classical physics predicted that a glowing hot object, like a piece of metal heated until it shines, should emit infinite energy at high frequencies. This was obviously wrong. Hot objects do not emit infinite energy. They glow red, then orange, then white, then blue as they get hotter. But the energy output at any given frequency is finite and follows a specific curve that classical physics could not reproduce. Planck found that he could get the mathematics to match the experimental data, but only if he made a strange assumption. He assumed that electromagnetic energy is not emitted or absorbed continuously in any arbitrary amount, but rather in discrete packets. Each packet carries a specific amount of energy determined by the frequency of the radiation. Higher frequency means more energy per packet. Lower frequency means less energy per packet. Planck called these packets quanta, from the Latin word for how much. He introduced a constant, now called Planck's constant, that sets the scale for how much energy each quantum carries at a given frequency. Planck himself was uncomfortable with this idea. He considered it a mathematical trick, a workaround to make the equations produce the right answer. He did not believe energy actually came in discrete chunks. He expected someone would eventually find a way to derive the correct radiation formula without needing quantization. But no one ever did. Then in 1905, the same year he published his special theory of relativity, Einstein took Planck's idea much further. Einstein was studying the photoelectric effect, a phenomenon where light shining on a metal surface ejects electrons from that surface. The puzzling thing about the photoelectric effect was that it depended on the frequency of the light, not the intensity. If you shone dim blue light on the metal, electrons popped out. If you shone bright red light on the same metal, nothing happened, no matter how bright you made the red light. This made no sense if light was a continuous wave. A brighter wave carries more energy, so a sufficiently bright red light should eventually knock electrons loose. But it never did. Only light above a certain frequency could eject electrons, and below that frequency, no amount of brightness made any difference. Einstein proposed that light itself comes in discrete packets, which we now call photons. Each photon carries a specific amount of energy determined by its frequency. A photon of blue light carries more energy than a photon of red light, because blue light has a higher frequency. When a photon hits an electron in the metal, it transfers its energy to that electron in a single event. If the photon's energy is high enough, the electron escapes the metal. If the photon's energy is too low, the electron cannot escape, no matter how many low-energy photons hit it. Each interaction is one photon transferring its energy to one electron. The process is discrete, not continuous. This was revolutionary and deeply confusing. Light is a wave. Thomas Young proved that with his interference experiment over a century earlier. Waves spread out, interfere, diffract. Light does all of these things. But light also comes in discrete packets that interact with matter one at a time, like particles. How can something be both a wave and a particle? This seems like a contradiction. Waves are spread out over space. Particles are localized at a point. Waves interfere with each other. Particles bounce off each other. These are completely different kinds of things. The answer, which took decades to fully work out, is that photons are neither waves nor particles in the classical sense. They are something new, something that does not exist in everyday experience, something that our language and our intuitions are poorly equipped to describe. A photon is a quantum of the electromagnetic field. It is the smallest possible excitation of the field at a given frequency. Not a tiny ball riding on a wave, not a miniature pellet shot out of a flashlight. A photon is what you get when you add the minimum possible amount of energy to the electromagnetic field at a particular frequency. It is an excitation of the field itself. Think about a guitar string. When the string is at rest, it is in its lowest energy state. It is not vibrating, it is just sitting there. Now pluck it gently. You have added energy to the string, and it vibrates at its fundamental frequency. You cannot add less than this minimum vibration. You can add more by plucking harder, which adds more quanta of vibration. But there is a smallest possible vibration, a ground floor excitation that you cannot subdivide further. The electromagnetic field works in a similar way, but it fills all of space rather than being confined to a guitar string. At any given frequency, the field can be in its lowest energy state, which we call the ground state or vacuum state, meaning no photons are present. Or it can be excited by one quantum of energy, meaning one photon is present, or two quanta, meaning two photons, and so on. Each photon is one unit of excitation of the field at that frequency. The field is the fundamental thing. The photon is what happens when you excite it by the minimum amount. This is why photons are not little balls flying through space. A ball is an object that exists independently. You can put it in a box. You can hold it in your hand. It has a definite size, a definite position, a definite trajectory. A photon is not like that. A photon is a process, an excitation, a specific kind of activity in the electromagnetic field. Asking where exactly the photon is before you measure it is like asking where exactly the vibration is on a guitar string. The vibration is spread across the whole string. It is not localized at one point. It is a property of the entire string. Similarly, a photon is a property of the electromagnetic field, and the field fills the space through which the photon travels. This is why light can behave as both a wave and a particle. It is neither. It is a quantum field excitation. When you do experiments that are sensitive to the wave-like properties of the field, like Young's double-slit experiment, you see interference patterns. When you do experiments that are sensitive to the discrete, quantized nature of the field, like the photoelectric effect, you see particle-like behavior. The photon is not switching between being a wave and being a particle depending on the experiment. It is always the same thing, a quantum excitation of the electromagnetic field. Different experiments simply reveal different aspects of that one underlying reality. This picture comes from quantum field theory, the framework that physicists developed in the mid-20th century to combine quantum mechanics with special relativity. Quantum field theory was built through the work of many brilliant minds, including Paul Dirac, who laid the theoretical foundations in the late 1920s, and Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, who shared the Nobel Prize in 1965 for their contributions to quantum electrodynamics, the quantum field theory of the electromagnetic interaction. In quantum field theory, every type of fundamental particle corresponds to a quantum field that fills all of space. Electrons are excitations of the electron field. Quarks are excitations of quark fields. Photons are excitations of the electromagnetic field. There is a field for every particle type, and every field fills the entire universe. These fields are not optional additions to space. They are part of what space is. They are the fundamental fabric of reality. This is a genuinely difficult idea to absorb, so let me try to make it concrete. We are used to thinking of space as a container, an empty room that things can be placed into. You put furniture in a room, you put air in a room, you put people in a room. The room itself is just the empty volume, the stage, the background. The things inside it are separate from it. If you remove everything, you are left with the empty room, just bare space, featureless and inert. Quantum field theory says this picture is wrong. The fields are not furniture placed inside the room of space. They are more like the walls, the floor, the ceiling. They are part of the room's structure. You cannot remove them and be left with bare space, because without the fields, there is no space in any physically meaningful sense. The electromagnetic field does not occupy space the way a table occupies a room. The electromagnetic field is part of what makes space the kind of space it is. The field is always there, at every point, even in the most remote void between galaxy clusters, even in the emptiest regions conceivable. It might be in its ground state, with no photons present, but it is present. It is woven into the location itself. This is why the question, how does light travel through empty space was so difficult for so long. People were imagining space as a bare container with nothing inside it, and then asking how a wave could cross that nothingness. But space is not a bare container. Space comes equipped with quantum fields as part of its fundamental structure. The electromagnetic field is already there, everywhere, before any light arrives. When a light wave passes through, it is not filling a void with something new. It is exciting a field that was already present, the way plucking a guitar string does not create the string, but sets an existing string into vibration. The string was always there, stretched across the guitar, ready to vibrate. The electromagnetic field is always there, stretched across the universe, ready to carry a wave. The vacuum is not the absence of the field. The vacuum is the field at rest. And a field at rest is still a field. It is still real. It still has properties. It is still capable of being excited. It is simply quiet. And here is where we arrive at one of the most profound insights in all of physics. What we call empty space, what we call the vacuum, is not truly empty. It is the ground state of all these quantum fields. The vacuum is what you get when every quantum field is in its lowest possible energy state. No photons, no electrons, no quarks, no particles of any kind. But the fields themselves are still there. They fill all of space. They do not disappear just because they are not excited. They are always present, always extending through every point in the universe, always ready to be excited into producing a particle if enough energy is available. This changes what empty means. When a physicist says a region of space is empty, they mean no particles are present. But the fields are still there. The electromagnetic field is still there. The electron field is still there. All the quantum fields are still there, sitting quietly in their ground states, permeating every cubic centimetre of the vacuum. Empty space is not nothing. It is the quietest possible state of a rich, multi-layered field structure that fills the universe. And the ground state is not perfectly calm. This is one of the strangest consequences of quantum mechanics. Werner Heisenberg's uncertainty principle, which states that certain pairs of properties cannot both be precisely determined simultaneously, applies to quantum fields just as it applies to particles. In particular, the field strength and the rate of change of the field cannot both be exactly zero at the same time. This means that even in the vacuum state, even when no photons are present, the electromagnetic field fluctuates. It jiggles. The field strength at any given point is not a steady zero. It is constantly flickering, fluctuating slightly above and slightly below zero in a random, unpredictable way. These are called vacuum fluctuations, and they are not theoretical speculation. They have been measured. They have real, observable, physical consequences. One of the most famous consequences is the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948. Casimir showed that if you place two perfectly flat, uncharged conducting metal plates very close together in a vacuum, they will experience a tiny but measurable attractive force pushing them toward each other. This force does not come from any charge on the plates. It does not come from gravity, which would be far too weak. It comes from the vacuum fluctuations of the electromagnetic field. Here is the intuition. The quantum vacuum is filled with fluctuating electromagnetic fields at all frequencies. Outside the plates, fluctuations of every possible wavelength can exist. But between the plates, only fluctuations that fit neatly between the plates are possible. Wavelengths that do not fit are suppressed. This means there are more fluctuations pushing on the plates from the outside than from between them. The imbalance creates a net force pushing the plates together. The force is tiny, but it has been measured with high precision and matches the theoretical prediction beautifully. The Casimir effect is direct physical evidence that the vacuum is not empty in the classical sense. Even when no particles are present, the quantum fields are fluctuating, and those fluctuations have measurable physical consequences. The vacuum has energy. Not a lot by everyday standards, but it is there, and it is real. Another measurable consequence of vacuum fluctuations is the Lamb shift, discovered by Willis Lamb in 1947. The Lamb shift is a tiny difference in the energy levels of hydrogen atoms that classical theory and even early quantum mechanics could not explain. The explanation turned out to involve vacuum fluctuations of the electromagnetic field interacting with the electron inside the hydrogen atom. The flickering fields nudge the electron slightly, shifting its energy levels by a tiny but measurable amount. The theoretical prediction, calculated using quantum electrodynamics, matches the measured value with extraordinary precision. Other calculations in quantum electrodynamics, such as the anomalous magnetic moment of the electron, agree with experiment to more than 10 decimal places, making it one of the most precise agreements between theory and experiment in the history of science. These effects tell us something remarkable about the vacuum. Empty space has structure. It has energy. It has fluctuating fields. It is not a blank, featureless void. It is the ground state of a fantastically complex quantum field system. And this ground state, while quiet by particle physics standards, is not silent. It hums with quantum activity. But here is a crucial distinction that we need to be very careful about. The fact that the vacuum has structure and energy does not mean the vacuum is a material medium. It does not mean we have reinvented the ether under a new name. The vacuum's quantum field structure is fundamentally different from any material substance. Air is made of molecules that bounce around, collide with each other, and transfer momentum. Water is made of molecules held together by intermolecular forces, flowing and splashing and carrying mechanical disturbances. The quantum vacuum is not like this. There are no molecules. There is no substance that flows or bounces or jiggles in a mechanical sense. The fields are not made of anything smaller. They are fundamental. They are the bottom layer of physical reality. When an electromagnetic wave propagates through the vacuum, it is not vibrating a substance the way sound vibrates air. It is propagating through the field structure of space itself. The quantum vacuum allows this propagation not because it contains stuff for the wave to vibrate, but because the electromagnetic field permeates all of space and supports self-sustaining oscillations as a fundamental property of its existence. The vacuum's permittivity and permeability, the constants that determine the speed of light, are properties of the quantum field structure of empty space. They are not properties of some hidden material. This is the answer to the question we started with tonight. How can empty space carry an electromagnetic wave? It can do this because empty space is not the featureless void we once imagined. It is the ground state of quantum fields that fill the universe. The electromagnetic field is one of these fields. It exists everywhere, at every point in space, whether or not any matter is present. When this field is disturbed, when a changing electric field creates a magnetic field that creates an electric field that creates a magnetic field, the disturbance propagates through the field at the speed of light. The field is not a medium in the way air is a medium for sound. It is more fundamental than that. It is part of the architecture of reality. It is woven into the fabric of space itself. And the photon, the quantum of light, is not a tiny object travelling through this field like a fish swimming through water. The photon is the field, excited by one quantum of energy. When we say a photon travels from a star to your eye, what we mean is that a quantum excitation of the electromagnetic field propagated from the star to your eye. The field was there the whole time, stretching across every point between the star and your retina. The excitation moved through it, the way a wave moves across a guitar string. The string was there before the wave and after the wave. The wave is something the string does, not something separate from it. Similarly, the photon is something the electromagnetic field does. It is not separate from the field. It is the field, in an excited state. This perspective resolves the ancient puzzle. We no longer need to ask what substance fills the void between the stars. The void is filled with quantum fields in their ground state. We no longer need to invent an ether to carry light. The electromagnetic field itself does the carrying, and it needs no substance to support it because it is fundamental, not derived from anything more basic. We no longer need to wonder how a wave can exist in nothing. The wave does not exist in nothing. It exists in the electromagnetic field, and the electromagnetic field exists everywhere. Let us step back and appreciate what we have learned tonight. We started with a simple observation. Sound needs air. Water waves need water. Seismic waves need rock. Every familiar wave travels through a material medium, and without that medium, the wave cannot exist. This seemed like a universal rule. Then we confronted light, which travels through the emptiest regions of the cosmos with no material at all. For centuries, this paradox drove physicists to invent an invisible substance, the luminiferous ether, to serve as light's medium. When experiments proved the ether does not exist, the paradox deepened. The resolution came in stages. First, Faraday showed that electric and magnetic fields are real physical entities that exist in empty space, not just mathematical abstractions. Then Maxwell showed that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, and this mutual creation produces a self-sustaining wave that propagates at the speed of light. The wave does not need a substance to travel through, because it is not a vibration of a substance, it is a vibration of the fields themselves, and fields can exist in a vacuum. Then quantum mechanics revealed a deeper layer. The electromagnetic field is a quantum field. Its excitations come in discrete packets called photons. The vacuum is not truly empty, but is the ground state of this field, and all other quantum fields, a state with structure, with energy, with fluctuations that have been measured and confirmed. Empty space is the quietest state of the richest structure in physics, and through all of this, the speed of light emerges not as an arbitrary number, but as a consequence of the vacuum's own electromagnetic properties, its permittivity and permeability, constants that are built into the fabric of space itself. The universe is constructed in such a way that electromagnetic disturbances propagate through it at exactly this speed. No faster, no slower. There is something deeply beautiful about this. The light that reaches your eyes from a distant star has travelled for years, sometimes for centuries, sometimes for billions of years. During that entire journey, no material substance supported it. No invisible ether carried it. The photons were excitations of the electromagnetic field, propagating through the quantum vacuum, sustained by the mutual creation of electric and magnetic fields, regenerating each other across the emptiness. The vacuum did not carry the light the way a river carries a leaf. The vacuum simply allowed the light to exist, because the electromagnetic field is part of what the vacuum is. When you look up at the night sky and see the stars, you are seeing electromagnetic waves that have crossed unimaginable distances of empty space. That light left its source years or centuries or millennia ago. It travelled through regions where there was nothing, no air, no dust, no gas, just the quantum vacuum with its quietly fluctuating fields. And it arrived at your eye perfectly intact, carrying the energy and information that allows you to see a star that might be 100 light-years away. Think about what this means the next time you step outside on a clear night and look up. Every point of light you see is a message carried by an electromagnetic wave that sustained itself across empty space for years or centuries or millennia. The light from Sirius has been travelling for about 8.5 years, its electric and magnetic fields regenerating each other step by step across 50 trillion miles of vacuum. The light from Polaris has been self-sustaining for about 445 years, each oscillation creating the next since before Shakespeare wrote his first play. And every one of those photons arrived at your retina not because some substance carried it, but because the electromagnetic field of the vacuum itself supported the disturbance from start to finish. You are not just seeing stars, you are seeing proof that empty space has structure. Every photon is a testament to the fact that the vacuum is not barren nothingness, but a physical arena with real properties. Properties that allow electric and magnetic fields to exist, to oscillate, and to regenerate each other across distances that would take light itself years to cross. The night sky is not just beautiful, it is evidence. Every star you see is a data point confirming that the vacuum supports field disturbances, that Maxwell's equations operate in the void between stars just as faithfully as they operate in a laboratory on Earth, and that the quantum electromagnetic field stretches unbroken from those distant suns to the surface of your eye. And here is perhaps the most astonishing part. The light that reaches you has lost nothing essential on its journey. The oscillation pattern, the frequency, the fundamental character of the wave is preserved across those staggering distances. A photon of yellow light, emitted by a star 4 light-years away, arrives as a photon of yellow light. The vacuum did not distort it, the vacuum did not degrade it, the vacuum carried it faithfully, because carrying electromagnetic waves is something the vacuum does as naturally and as effortlessly as the ocean carries the shape of a wave across its surface. Except the vacuum does it without any substance at all. Just fields. Just the quiet, omnipresent, fundamental fields that are part of what empty space truly is. This is the quiet revolution that began with Faraday's lines of force and ended with quantum field theory. We spent centuries searching for a substance filling the void, and what we found instead was something deeper. Not a material, not a medium, not an invisible cosmic jelly, but the ground state of the most fundamental structures physics has ever uncovered. The vacuum does not carry light the way air carries sound. It carries light the way mathematics carries truth, not by being made of the right material, but by having the right structure. What we call nothing turns out to be one of the most extraordinary somethings in all of physics, and the proof is in every beam of starlight that crosses the void to reach your eyes. The wave needs no medium because the field is already there, everywhere, always, woven into the very structure of space. That is how empty space carries an electromagnetic wave, not by being a hidden substance, not by being a disguised material, but by being something far more fundamental than any material could ever be. A quantum field, filling the universe, capable of supporting disturbances that travel at the speed of light, carrying energy and information across billions of light-years, without ever needing anything more than the bare, beautiful fabric of reality itself.